So now let's apply the divide and conquer approach to our search problem. So we can take advantage of the fact that our list is already sorted. So instead of searching the whole list, we can look at the middle element and know whether or not which part of the list we need to search for. So for example, if we need to look for 9932, if we look at the middle element of the list, we see that it's around 6,000. So our element should be in the upper half of the list. So that is what this code essentially does. So it finds the midpoint over here, and then depending on the midpoint, we modify which where our search loop starts. So it either starts at the middle if we find that the element we're looking for is greater than the middle element, and we search the lower half otherwise. But doing that, we uh, don't really reduce the number or the time complexity, since when we have the total list size, our asymptotic notation still tells us that it runs in linear time. So what can we do? So remember that in divide and conquer, once we partition our problem, we don't have to stop there. We can partition it again, and partition it again, and partition it again. So let's we can check the middle element or partition our partition our lists for a indefinite amount of time or indefinite amount of times up until we get let's say a one element list. So when we only have an one element list, looking for something in that one element list is trivial since it's either there or it's not. So in this code below, so up here is the base case, which we'll talk about later. So here, uh, the midpoint is first calculated for, taking into account the end and the start of the array or the index of the elements. So when our key or the element we're looking for is greater than the middle element, we search for the element in the upper half. So that's from mid to end. So for example, here, if our starting element our starting index is index 0, and our final index is the size of the list, which is n. So that's where our n is. So our middle element here will be 1, 2, 3, 4, 5. Let's say 6, 7, 6, 9. So since 9932 is bigger than 6769, we will be searching for the element in the upper half of our list. And then since it's the upper half of the list, we apply binary search again, but this time we start at the index of the middle element up until the last element. So otherwise, we will be searching this list if it were smaller. So the process continues again. So let's remove this. So applying binary search to this subsection, we can say that our midpoint is probably here. And then we check again if the index of the element we're looking for is in the upper half or in the lower half. So in this case, it's in the upper half. So the process repeats itself again and again until we reach the base case wherein n minus start is equal to 1, or we have just one element. So if we have just one element, the element we're looking for is either there or it's not. So it's a constant process. So we just have this conditional to do that. Then otherwise, if end apparently becomes less than or equal to start, the list is empty. So that's basically how binary search works. So I'm not sure why the result here is -1. I think it just needs to be run again. It's running, it's running. Okay, so we get the index of 9932, which is at index 9. So we can uh, use input a different number, 1503, then we get index 0. Now, if we input an element not in the list, say 1000, it basically results in -1. So you can play with this yourself. So more on binary search, its analysis in the next videos.